In this lecture, we're going to explore the standard deviation visually and through the mathematical expression of it a little closer. And so when we start to talk about the standard deviation, we have to come back to the normal distribution. And the standard deviation, by definition, covers approximately 68% of all the scores in a distribution. And so when we talk about the variability of a sample of one standard deviation around the mean, we're talking about that one standard deviation capturing approximately 68% of all scores. Now, what we're looking at here in this example, if we have a sample of individuals in which we were sampling the age, and we determined that the average age of the individuals in this sample was 80 years, with a standard deviation of plus minus 5 years, how is that represented on the normal distribution? Well, what we do here is we label the 80 years as the average. So this is an X with a bar on top of it. The bar has been moved here in PowerPoint, but make sure that there is a bar on top. And we have the limits of the standard deviation. And so it's important to note that when we talk about the variability, it's a plus and minus around the average. And so we have an average of 80 plus 5 years, so we're looking at 85 years, as well as minus 5 years, which is 75 years. And so the limits of one standard deviation, as you can see, there's plus and minus 5 years around the average, so the total length of the standard deviation in this case is 10 years, or 2 times the standard deviation. And so this will capture 68% of all the scores. Recall that when we examine a distribution, this is the only time we see the dependent variable expressed along the x-axis, and the number of scores corresponding to each age, the number of people corresponding to each age, is plotted along the y-axis. And so the area underneath the curve here is the total number of people that have ages between 75 and 85 years old. So given the fact that one standard deviation captures 68% or approximately 68% of all the scores, we can also conclude that 32% of the scores reside outside of the standard deviation, as we approach the positive directed tail and the negative directed tail. So I say negative directed tail pointing in the negative direction. Of course, these are not negative ages, but we have the lower end and the higher end. If we count up all the people in this segment, count up all the people in this segment, that would approximately 32% of all the people. Now, if we have a distribution that is not exactly fitting to the standard normal distribution, we have a different shape. The standard deviation is still defined by capturing approximately 68% of all the scores. So the same rules apply. It's just that the actual values of the standard deviation would be farther away from the mean. So if we begin by taking a look at a leptokurtic distribution, so this is still symmetrical. It still follows the same pattern as we observed on slide 38 with the normal distribution. It's just that the scores are more concentrated towards the mean. And if the scores are more concentrated towards the mean, then if we take a look at the standard deviation, the actual values, we see that they will also be closer to the mean. And so in this case, we have a mean of 80 years and a standard deviation of plus minus 3 years, since we're 3 units away from the mean on the positive side and 3 units away on the lower side. Likewise, with a platykurtic, a more flatter type of distribution, symmetry still applies here, and we have a wider standard deviation, still capturing 68% of all the people in this sample or population, but the standard deviation is now plus minus 8 years. So we have 8 years above the average, 8 years below the average. So this represents, so what we've talked about so far is a visual representation of the standard deviation that captures, that describes how spread out the scores are in a sample or a population. Now, when we express this mathematically, when we talk about the standard deviation, the symbol S subscript X, that is implicitly stating one standard deviation unit, but we never write the 1 in this case. But we always know that there's going to be a 1 there. So if we wish to find the scores that are plus minus 1 standard deviation about the mean, we'll go with our regular example, with the example we've been working so far. In our sample, we have a sample average of 80 years, a standard deviation of 5 years. And so we just apply the equation here where we take the average, x bar, and we subtract 1 standard deviation unit, and that gives us 75 on the lower end, and we add the same standard deviation to the average, giving us the upper limit of the standard deviation. Now if we draw a vertical line through the equal signs, we see that we have a left-hand side and the right-hand side to these equations. And so understanding that the equal sign explicitly tells us that 75 is a true statement and the left-hand side is a true statement, but it's expressed a little bit differently. On the left-hand side, the equation expression is in what we call normal distribution units. And this is the mathematical expression of the standard deviation. On the right-hand side, with the actual numerical values, the units are in the original measurements. And the original measurement unit here in our example is 80 years, 5 years, plus minus 5 years. And so a little bit of theory here in terms of understanding population variability and how we will modify this slightly when it comes to tracking the variability of a sample. So when we wish to estimate the population variance and standard deviation, we have the assumption that the sample variance will often underestimate the population variance. And so that's something that is something that has been mathematically problematic over the years in trying to gain an understanding of linking the sample statistic to the population parameter. So based upon our previous video where we calculated the variance, so S squared is a sample variance, which we talked about in an earlier video, that presents units that don't make sense, but as a mathematical way that will get us to the calculation of the standard deviation, in which we just simply take the square root of both sides. But this presents what's called a biased estimate, and when we use this approach to calculate the sample standard deviation, it will tend to underestimate the population parameters in theory. And so what we wish to do is to gain an unbiased estimate of that population variability. And so we take our sample variance. Now, slight difference here. Here I have a lowercase s to indicate that we're going to get the unbiased approach. So the equation is the same with the exception of the denominator. Instead of dividing what's called the sum of squares, so in our numerator, we call this the sum of squares. Instead of dividing it by the sample size, we divide it by the sample size subtract 1. And this is called the degrees of freedom. And this is something that you will see throughout the various statistical techniques that we'll address in this course. So for example, if there were 20 individuals in our study in which we measured age, and so our sample size is 20, but our degrees of freedom will be 20 minus 1, will be 19. What that tells us is that out of the 20 samples, 19 of the samples are free to take on any value along our measurement tool, and once we have all 19 that obtained that were free to vary, then the final value is not going to be free to vary. So understanding that we have an average, we have 19 values, that 20th value will be a prescribed value in theory. So moving forward, we will often use the degrees of freedom approach, where we take the sample size and we'll reduce it by 1. In some cases, we'll reduce it by 2 units, but that will be specific to the statistical technique that we cover. Another common helpful and way to track sample variability is something called the coefficient of variation, and this is very often used for interval or ratio data. And based upon the equation here, you see that the coefficient of variation is equal to the sample standard deviation. Okay, so we use lowercase s, so we have the sample standard deviation. Note that I didn't put the subscript x here, but the lowercase s or the lowercase s with subscript x are used interchangeably. So depending upon the source you read, you will see it presented in both one or two of those manners. So the standard deviation is divided by the sample average. Because the sample standard deviation in our example was a measurement of age, and the units are years, as is the unit for the average age, which is years, the units cancel out, and we're left with a ratio when multiplied by 100% will give us a percentage sense of that variability. And so one of the advantages of the coefficient of variation is that it presents a unitless measurement. And so the units are eliminated, and in doing so, we are now able to compare different measures in terms of variability. And that's going to be problematic if we don't eliminate the units, because if we wish to measure household income variability and age variability, we cannot compare those two in terms of their raw units. We have to eliminate the units so we can do a comparison between those two variables. The coefficient of variation is a very effective way to do that. The coefficient of variation is also presented as a proportion of the mean, and it becomes a little bit easier to visualize as a percent if we make that reference back to the mean. Oftentimes it's difficult to get a visual understanding, a mental understanding of that standard deviation in the original units, but when presented as a percent, it often helps with the interpretation. So this ends this video on the basis of the standard deviation.